Swayam Prabha. Digital India. Educated India.
Welcome to the lecture today. Today's lecture will be slightly more physical, slightly less mathematical, okay, compared to last time we only had equations. So, we will have a little bit more of physics to make sure that we realize that all the maths we are doing actually has some physical motivation, okay. So, the grand objective that we have is to find the drag force on a sphere, okay. And most of you have done experiments in your fluid mechanics lab, where you look at, you drop a small spherical ball made of some metal in a cylinder. The ball is going to keep falling down. Initially it will accelerate, after some time it attains a terminal velocity, right. The reason why it attains a terminal velocity is because there is a balance of forces. So, there is a drag force which is going to be in the direction against the motion, and then there is a buoyancy force which is going to be the upward direction. So, all of these balance each other, the buoyancy force and the drag force, and then you have the weight. So, when these forces balance each other, there is no net force and there is no acceleration, and you have a terminal velocity. So, you possibly use this, and what you have done is use something called a drag coefficient to calculate drag forces on different kinds of objects, okay. So, that's, you have some charts, and you look at those charts depending upon the Reynolds number, you find out what the drag coefficient is, then you calculate your drag force on a cylinder, on a sphere, on a flat plate. So, what our objective is to try and see if we can find analytically the solution for the drag force, okay. In fact, in the limit of very low Reynolds numbers, where inertial forces are not there, when you have the creeping flow or the Stokes flow approximation, the inertial terms can be neglected. So, those are the non-linear terms. So, they can be neglected, and what you have is basically a system of linear equations, okay. So, we think because the equations are linear, we can hope to get an analytical solution. So, when you get an analytical solution, you will get some insights as to what are the different kinds of contributions which are going to the drag force. So, the idea is to look at this creeping flow limit, because that makes the whole system linear. Then you get an analytical solution, and you will say the drag force is composed of different parts, for example, and you understand it better. So, when you actually do an experiment which is not in the creeping flow limit, you may be able to interpret your results in a better way, because you may get some other peculiar results. So, that is the thing, okay. So, we are looking at regime, okay. Basically Reynolds number very much less than 1, we neglect the inertial terms, our equations are linear, and we get an analytical solution. In fact, so the idea is that this is a two-dimensional flow problem, okay. And what I am talking about here is, I mean, this is your typical experiment that you have. This is the cylinder, this is the cylinder containing liquid, this has water inside it, and you drop this metallic sphere which is falling down, okay. And since the if the diameter of the sphere is much smaller than the diameter of the cylinder, then what we can do is we can neglect the effect of the confinement because of the cylinder. Okay. So, basically what I am saying is, if the diameter of the sphere is much lesser than diameter of the cylinder, so you have the cylinder here, you have the sphere here, we can neglect the wall confinement, okay, and treat the system as a ball falling in an unbounded liquid. Okay. Of course, if the diameter of the sphere is much comparable to the diameter of the cylinder, then the wall of the cylinder has to be considered. You can't make this assumption of unbounded liquid. Okay. So, basically what I am saying is, so we are going to clearly do the problem of things in an infinite domain. So, I do not have to worry about wall effects. So, if you want to really do about wall effects, then you have to do something more computational. Okay. So, to get insights, we just stick to this. The other problem is, in the actual problem, we are interested in what is the drag force and which is going to decide the terminal velocity. Okay. So, at that time the sphere is actually moving down, okay, at a constant velocity. So, rather than talk about the sphere which is moving down at a constant velocity, I can change the reference frame. I can look at the sphere as, because the drag force is going to be arising because of relative motion. Okay. What you do is you make your life simple, you treat the sphere as being fixed and say the liquid is moving at the velocity of the terminal velocity. Okay. So, either the liquid is stationary far away and the sphere is moving at a constant velocity. I am saying it is equivalent to a sphere being stationary and the far field liquid velocity being the terminal velocity. Okay. Both of these are equivalent. Okay. So, rather than solve the problem in a stationary reference frame. Stationary reference frame means I am outside, the ball is falling, I am analyzing that system. Okay. We analyze the problem in a frame of centered at the sphere center, which is fixed and the fluid moves at a constant velocity far upstream. That is, as r tends to infinity, we have u in the flow direction, u in the, I do not know, this is what k direction is equal to u infinity. Okay. So, what I am saying is, far away the liquid is moving at this velocity. Okay. That is the problem. So, we are going to look at, so we are not going to worry about reference frame, I mean the sphere moving, because I have to keep tracking the sphere. I am interested in the drag force, that is my objective. So, and I just changed my frame of reference, understanding that the drag force is coming because of the relative motion. Okay. That is one thing. Now, if you remember, I mean something earlier, what you did, CD for a sphere is given as 24 divided by RE. This is a drag coefficient, okay, and basically we are trying to, and this is valid only for low REs, okay. I hope I remember this right. I wanted to basically make the point that this is very analogous to this friction factor concept which you have used in flow through a pipe, for example. So, friction factor F is given by 16 by RE or 64 by RE depending upon how you are defining a friction factor. This friction factor is for flow through a pipe, okay. Again, this is valid only for laminar flow. So, this friction factor is basically arising because of viscous stresses, okay. There is a shear stress at the wall because of viscosity, and that is what is causing the pressure drop, and that is basically giving rise to the friction. Now, when you had to solve this problem, what you did is you were looking at the problem of laminar flow, right. I mean, that's, if you recall, or if you do not recall, you can go back and check. We calculated what the parabolic laminar flow velocity profile is, then we calculated what the shear stress is, and then we defined the friction factor, okay, and that is used for finding out the pressure drop. And only thing is, in this case, that the flow was one dimensional, and we could get this nice beautiful laminar profile. In the spherical problem that we are going to discuss, it is basically extending the same approach to a flow which is two dimensional, where there are two velocity components, okay. So, here the flow is one dimensional, and we find the parabolic velocity profile, then we find the shear stress, okay, and then we find the friction factor. I am going to use the same thing here. I am going to say, I mean, this laminar flow, if you remember, we really did not assume low Reynolds number, because we assumed fully developed flow, and automatically the inertial terms dropped out. So, in some sense, this is a one dimensional creeping flow problem, because the inertial terms did not contribute, okay. So, here what I am going to do is, I am going to do a 2D problem, find velocity field, okay, and shear stresses, okay, and the drag force. This is what we are going to do, okay. So, I just wanted to point out this parallel, the similarity between what you have done earlier and what you have done now, and the only reason why I am able to do this is because in both the cases the inertial terms are dropping off. If the inertial terms do not drop off, I will not be able to do the thing that I am going to be doing today, okay. And inertial terms, remember, are the ones which are non-linear, which are the ones which are making it necessary for us to use numerical methods to solve Navier-Stokes equations. So, what I am doing is I am just making my life simple by making this approximation. So, in the spherical coordinate system, the three coordinates are r, theta and phi. These are the three coordinates, okay, and it's not Cartesian is easy to visualize, cylindrical is also easy, but spherical, I mean, you have to think, otherwise you have to just look at this is a sphere, and this is of course x, y and z, but we are not working with x, y, z, okay, we are working in r, theta, phi. So, any point here is specified by r, theta and phi instead of x, y, z. What is r? R is the radial direction. Tells you, r tells you what is the distance from the origin. Okay. Theta is the angle which is measured in this direction. This is theta. This angle, how do I indicate this? This is theta. Okay. This angle is theta. So theta will go from 0 to pi. So point is 0 is less than theta is less than pi. Some people like to go minus pi by 2 to plus pi by 2. It does not matter. Okay. I am saying this is theta equal to 0 and goes up to pi. And the third angle phi is the one which is telling you what is your azimuthal position around the sphere. Okay. Phi tells you the azimuthal position around the sphere. Now, I think so you can imagine phi is the angle along this direction. Okay, I don't know how to draw this, so I'll just say this is phi. Okay. So now we have the 3 coordinates, and like I said, we want a 2-dimensional flow. Okay. So in spherical coordinates, when people talk about symmetric 2D flows, normally they talk about axisymmetric flows. That means flows are going to be symmetric about phi. Okay. So here the flow is axisymmetric, implies d by d phi is 0 and v phi is 0. Okay. This is very similar. So this is the coordinate. So if I have a ball here, the phi is this angle. Phi is the angle which I am going around the sphere. Theta is the angle which I am going in this direction, and r is the radial direction. Okay. So I mean, you have to look at better ways of visualizing this, but spend some time and think about it so you understand what I mean by phi symmetry. So by phi symmetry, I mean the velocity here at a particular phi is the same as the velocity here, is the same as the velocity at another phi, but there is variation in theta. Okay. So basically the problem we have is the velocity has 2 components, Vr and V theta. Okay. It makes sense, right? I mean, clearly you need to, the liquid is coming here, the liquid is coming, let us say from the bottom. Okay. When it comes closer to the sphere, it is going to slow down. So, it is going to be a function. So, the radial velocity is going to be definitely there, is changing with the radial position. As it comes closer, velocity is going to change, and as when it goes around like this, the velocity is going to change, because it changes the theta direction, then it goes back to getting V infinity. Okay. So basically the point is, in this coordinate system, the 2 independent variables are r and theta. Okay. And the 2 dependent variables are Vr and V theta. So this basically is something similar to what we did in cylindrical geometry, where we talk about axisymmetry, where we neglect the theta dependency. Okay. So that is something which you have to understand. So here we neglect phi dependency. I don't know if I wrote this already. Okay. And in our problem, Vr is a function of r and theta, V theta is a function of r and theta. It does not depend upon phi. At any phi, V theta is the same, Vr is the same, as long as r and theta are the same. Okay. So at this position, Vr and V theta are the same, here Vr, V theta are the same. So there is no point in me telling you this 10 times, you have to think, okay, and visualize. So I told you we have a situation where we have creeping flow, inertial terms are neglected, and if you wanted to solve this problem of the sphere is fixed now and liquid is flowing around. Okay. So I am going to, so for creeping flow, we have 0 equals minus gradient of P plus mu del squared V vector. This is a very gentle notation which I have written, okay. The inertial terms, this is Navier-Stokes equations without the this thing, and of course you have the divergence of V equal to 0, okay. Now, what I want to do is I want to exploit the fact that this flow is 2 dimensional, and rather than work in the primitive variables u v or Vr, V theta and P, I want to go to the stream function formulation, which is why I did whatever I did last time. So, given a stream function, you can calculate what the relationship is between velocity and the stream function, right. Velocity I said was curl of psi E k. So, we do the same thing here, okay. So, basically because it is 2D, we use stream function formulation, stream function and vorticity, okay. And I am not going to go through, so whatever I did yesterday for Cartesian coordinates and cylindrical coordinates, you need to do it for spherical coordinates, okay. And it will turn out that velocity Vr is I think it's fine, and V theta is 1 by r sin theta d psi by dr. I think this is right. I get confused whether there is sin squared or not, but I think it is only sin. Maybe some of you guys who have mobile phones can check and let me know whether it is sin squared. Yeah? This is minus here. Yeah, that is right, this is minus, but it is only sin, not sin squared. So, this is what you should get if you do what I did yesterday for spherical coordinates, okay. Remember, the first step is we relate V as curl of psi E phi, okay, and curl has the matrix notation. How do you find the matrix notation? By finding curl of V. So, basically you can do that, okay. How did I get this? I got this by V as curl of psi E phi, and curl in spherical coordinates has a matrix representation. You can use that, number 1. And how do you find that? By doing a first principles cross product term by term and remembering that the unit vector changes, okay. So, I mean, I am not going to do this because that is your homework. So, now I have the velocity, okay, in terms of the stream function, and because it is the creeping flow limit, like we did derive last time, we had got del squared del power 4 psi equal to 0 for the creeping flow. Here, for in the creeping flow limit, we get e power 4 psi equals 0, okay. I mean, again, this is something which you have to do exactly like what I did yesterday. Yesterday I did something and I got del power 4 psi, but this time when you do it, you will get e power 4 psi, okay. And that is the point I was trying to tell you yesterday, that there is a difference in the spherical coordinates. You are not going to use del, you are going to use E for this calculation, okay. And the reason is the spherical coordinate has the system has a slightly different property, which if you are interested you can read and figure out. So, this is not del power 4 psi equal to 0, okay. I want to emphasize this. For Cartesian and cylindrical, you will use del power 4. So, now, so what is this E squared? So, we have, what is this E squared operator? So, again this is the same thing like what we did in the math course where we talked in terms of operators. Okay. So, basically when I say E square psi, E square is an operator which is acting on the stream function psi. Okay. And this is defined as this thing, this differential operator acting on psi, and you do this exactly for spherical coordinates like what we did for the other two coordinate systems yesterday. Okay. That is how you would get this. I think it is right. Huh? So, now for in the creeping flow limit, okay, in the creeping flow limit, e power 4 psi is 0. So, what does this mean? It means E squared of E squared psi. This means E squared of E squared psi is 0. Okay. So, I mean, because some of you were not there in the math course last time, so I am just taking some time to explain this thing. This is written as d square by dr squared plus 1 by r squared sin theta d by d theta 1 by sin theta d by d theta. This is the first E squared, okay, and this is operating on this guy. Of psi equal to 0. So, this equal to 0 comes because the inertial terms are dropping off. No, I am expecting that you people will derive this E squared, okay, using whatever I did last time, and all of you should do it. So, the idea is I find the second derivative with respect to r plus derivative with respect to theta, I do this operation on psi, I will get some function. On that function again I am operating with this. That is what I mean by E squared of E squared. E power 4 is E squared of E squared. What does it mean? Take psi, second derivative with respect to r plus derivative with respect to theta divided by sin theta, derivative with respect to theta again multiplied by sin theta by r squared. Add these two, you will get some other function. On that function again do the same operation. Okay. That is the meaning of e power 4 psi, and this is what we have to solve. Okay. So, this is the stream function which we have to solve for this thing, and the advantage like I told you is we have eliminated this pressure, this business of having to find pressure using continuity and all that is gone. I only have to solve for one equation. Only problem is now it is a higher order equation. Okay. It is a fourth order equation, not a second order equation, because if you want to do it vectorially, one way to do it is take this vectorial equation and take the curl of this equation. Curl of gradient of anything is always 0. So, you will get mu times del square of curl of V equal to 0, and then V you write in terms of stream function and you get a fourth order equation. Understand? Second order equation, when you take a curl you get third order, you write the velocity in terms of stream function, you get one more order. That is how you get a fourth order. Okay. So, the point I am trying to make you is make you think, you know, about things from different perspectives. Anyway, so okay. So, in order to solve this differential equation I need boundary conditions, right, and now remember the problem is one of the sphere is here, and let us say the sphere has radius of a on the surface. Okay. So, clearly you have to satisfy the no slip condition and the no penetration condition. So, the no slip condition implies, what does it imply? V theta is 0 for all r at r equal to a. Okay. if V theta is 0, that means d psi by dr is 0. This means, this implies d psi by dr is 0. Okay. And what about the other thing? The no penetration condition. The radial component of velocity is 0. Implies Vr equal to 0, which means d psi by d theta is 0. Along the surface, psi is not changing. Okay. Psi is constant along the surface. Psi equals constant along the surface. What that means is there is one streamline which is going to be hugging the surface. Okay. If on the surface psi is not changing, remember psi is constant along a streamline, right. So, that means there is one streamline which is going to be hugging the surface. Okay. So, I just was hesitant to erase that, but anyway I am going to erase it. So, there is one streamline along the surface of the sphere. Okay. And so, on the surface is going to be constant. So, d psi by d theta equal to 0 means psi is constant, and I can take, like I said earlier, psi equal to 0 along the surface as a reference value. Okay. As a reference, I can take psi as 0. But everything else is going to be relative to this reference. Now, so I need the boundary conditions far away. Okay. The far upstream conditions. That is, far upstream means as r tends to infinity. Far away, what do I expect? I am expecting far away, I have my sphere here, far away my flow is going to be uniform. I have uniform flow past the sphere. Just like your boundary layer on a flat plate, you have uniform flow far away and you have some boundary layer effects near the plate. Okay. So, something similar, far away the thing is uniform. What I am going to do, just to make it easy, I am going to say that the flow is coming from top to bottom. Okay. Sorry man, I am going to make this arrow the other way. I should have thought about it better, because I think it helps me explain it easier, because my theta is in that direction. Okay. So, this is my theta direction, remember. Okay. Now, I want my boundary conditions on Vr and V theta. What I have is a uniform flow, okay, uniform flow coming down this way. Okay, it does not really matter, up or down does not matter, but for me, it is easy for me to visualize it this way. So, this is the vertical component of velocity, okay, which is uniform, everywhere is the same, and I think I said that was equal to u infinity. I am going to resolve this in the r direction and the theta direction. Okay. This is my r direction and this is my theta direction, and they are perpendicular to each other. This is theta direction. So, the velocity Vr, which is the radial component of velocity, okay, at any point is going to be specified by the corresponding theta value and the phi value. Okay. Phi we do not worry about. The Vr is going to be given by u infinity cos theta. because that is the angle theta. Theta is measured with respect to this. Okay. And V theta, I mean you can very close your eyes and blindly write this, is minus u infinity sin theta, because theta is in that direction. I am resolving this velocity in these two directions, and this is the negative theta direction. Okay. This velocity has this component and this component, this is r direction, this is theta direction, this is negative theta direction, because theta is clockwise. So these are small things you people have to understand when you are doing the calculation, which is why I am explaining it explicitly. Okay. So theta I am measuring counterclockwise, but this velocity is resolved as ER and E theta, and this is in the opposite direction of the theta. That is the reason I am having this minus sign. So I mean these are small details you worry about. Okay. So now this is going to be minus, okay, these are the boundary conditions at r tending to infinity, because my problem is in terms of Vr and V theta. Why do I want Vr and V theta? Because I am going to now convert this to stream function, okay, because and I already had that relationship. So V theta is minus u infinity sin theta, which is equal to 1 by r sin theta, again with a minus sign, d psi by dr. This is the, what have I done? This is the relationship between V theta and stream function. This is how V theta is far away. I found that from the physical problem. Okay. What is the objective here? The objective is to convert this boundary condition to psi. So I want to know what, because I am solving for psi in the stream function vorticity formulation. I want to get the boundary condition on psi. Okay. So I am going to set these two to be equal and calculate psi. Okay. And you can just integrate this. So what did I say? Yeah, integrate this equation, the third and the second term. So psi will be u infinity and integrating with respect to r. So theta is treated as constant, theta times r squared divided by 2. That is what you get as r tends to infinity. So no slip, no boundary, no penetration condition at the wall, far away it is uniform flow. I have resolved it in the r and theta direction, okay, converted that, and you can do the same thing. You can use this also to find psi. That also can be done. You should get the same result. Okay. I use the second equation. You can also use this first equation and trying to find out what is psi. Okay. And using the same method, you better get the same thing, right? If you get a different answer, you have a problem. So I mean, I will leave it to you to check if you get the same thing. So we should get the same expression if we use what? The definition of VR. Yeah. To find psi. Okay. I leave it to you to do it. Now, so basically now I have the boundary conditions and I have the differential equation, and I should be in a position to solve. Whether I have enough boundary conditions or not, we have to see, because it looks like I have a fourth order equation, I have very few boundary conditions. Okay. So we have to proceed further, but then we are going to use things like symmetry and all that, so maybe we are in good shape. Okay. Boundary conditions are clear. So how do you solve? So this is a partial differential equation, and there is only one thing we know how to do when you have a partial differential equation with two variables, which is use something like separation of variables, right? So if you look at it, the equation is homogeneous, e power 4 psi equal to 0, then you have psi equal to 0 at r equals a, you have d psi by dr equals 0 at r equals a, and only thing psi is u infinity r squared by 2 sin square theta at r tending to infinity. This is the system. Okay. So, being a partial differential equation in independent variables r and theta, what I am going to do is I am going to seek the solution analogous to separation of variables. It is not exactly what we did the classical separation of variables, but we will say, look, I am going to use some physics, some maths, and then combine this thing and get a solution. Okay. If it works, it works. So, we seek psi as f of r multiplied by sin squared theta. So, I have separated the variables, I have separated the r dependency and the theta dependency. What is the motivation, what is the logic? I mean, by choosing this for some function multiplied by sin squared theta, this motivation is coming from this, because far away I have my psi has to behave like this. Okay. As r goes to infinity, my psi has to behave as u infinity r square sin square theta by 2. So, I am saying if it has to behave far away as sin square theta, I am saying I am going to assume the theta dependency to be of the form sin squared, because r I have to satisfy the boundary condition a also. Okay. So, I am not doing the I am not saying the r dependency is r squared. So, by looking at this thing, I am trying to see, of course, it may turn out that this assumption is not valid, such a solution does not exist, but that I can find out only after I go through the entire process and figure out it is not working. If I am lucky, I mean this will work, I can find a solution. Okay. So, it is not that I am guaranteeing you a solution, I am saying, look, because of this boundary condition dependency of sin squared, I am assuming this dependency is also sin squared. I do not know what is f of r. So, what I want to do now is substitute this in my equation. Okay. And I am going to do the substitution in E squared. So, I look at E squared psi equals 0, and you know of f of r times sin squared theta is what I have. Okay. This E squared psi is not equal to 0. This is E squared psi. E squared psi is this. E power 4 psi is 0. Okay. E squared psi is not 0. So, I am just writing E squared psi. This is E squared. Okay. I hope I remember it right, and this is my form for psi. And how do you calculate this? I calculate this as second derivative with respect to r of f. So, this will be f double dash f by dr squared sin squared theta plus 1 by r squared sin theta times d by d theta of 1 by sin theta, and f is coming, I am differentiating with respect to theta. So, f is a constant. So, f comes out. Okay. I write f. What is the derivative of sin theta with respect to theta? That is cos theta. Clearly something is wrong. What is wrong? Yeah, louder. I have to differentiate sin squared theta. Okay. This f of r multiplied by, it is not sin, it is sin squared. I have to differentiate sin squared theta, that is 2 sin theta cos theta times f. or maybe I put F here, man. I put F here, okay, because I don't want to confuse over there. So now what is this? Sin theta cancel. I get 2 cos theta, and I differentiate this with respect to theta. I get minus sin theta again. I get minus 2f divided by r squared sin squared theta equal to 0, not equal to 0, equal to that, okay. So this is basically sin squared theta multiplied by f double dash minus 2f divided by r squared. This is just E squared, okay. So all I have done is just done the substitution here. What we want to do is, so basically separation of variables, what do? We convert the PD into an ODE. So I have converted this to an ODE. Now we need to sit and apply E squared again, okay. And when you apply E squared again, because what I am interested in is E power 4. So E power 4 psi equals 0, this is E squared psi. E squared psi is that you will get something like f d square by dr squared minus 2 by r squared operating on d squared by dr squared minus 2 by r squared operating on f. So you operate on this, you get that. Again you have to do the operation here, okay. You will get a 4th order equation in f, okay, which we have to solve for. So just to give you, cinema they have some teaser and all that, so I am going to give teaser. What we are going to do next class is find the stream function, find f of r, find the stream function, find the velocity field, okay. After we find the velocity field, we get the pressure, okay, and because you have to satisfy the creeping flow Navier-Stokes equation. So I have the velocity field, I have the pressure information. Then along the surface, I have to calculate what are the forces which are contributing to the force, the drag force, which is you will have the normal component, you have the tangential component. Both the components are going to contribute, okay, and then you find what is the total contribution, because it is going to vary from point to point. So you have to integrate along the surface of the sphere, and then you get your expression for Stokes law for finding the drag force, which you have been using all this while, some 6 pi mu AV, something like that, okay. That is what we are going to get. So, but this is the procedure we are going to follow, okay. Thank you.